last time we were able to solve a system of linear equation using the method of Gauss-Jordan as well as the Gaussian elimination. Now we are ready to solve real-life problems, and we are going to apply what we learned last time in solving the system of linear equation. So lesson 1.3 is about applications of systems of linear equations. The objectives for today: set up and solve a system of equations to fit a polynomial function to set of data points, and set up and also solve a system of equation to represent a network. Systems of linear equations arise in a wide variety of applications. In this section, you will look at two applications. The first application shows how to fit a polynomial function to set of data points in the plane. And the second application focuses on networks and Kirchhoff's laws for electricity. First, we deal with polynomial curve fitting. Let us consider endpoints in the xy plane. So we will have here a set of ordered pairs x sub 1, y sub 1, x sub 2, y sub 2, up to x sub n, y sub n, which all represent a collection of data, and you want to find a polynomial function of degree n minus 1, such that we will have your p of x is equal to a naught plus a sub 1x plus a sub 2x squared plus dot 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 plus a sub n minus 1 times x raised to n minus 1, whose graph passes through the points. This procedure is called the polynomial curve fitting. When all x coordinates of the points are distinct, there is precisely one polynomial function of degree n minus 1 or less that fits the n number of points as shown in figure 1.3. So we see here that we're given several points with different x coordinates. You have your x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, and x sub n, y sub n. Now, how do we find the best fit for a given set of points? Example, determine the polynomial p of x, which is equal to a naught plus a sub 1x plus a sub 2x squared, whose graph passes through the points 1, 4, 2, 0, and 3, 12. So what we need to do is simply substitute, say, the value of x and y into the particular equation. So for example, p of 1, okay, when x is equivalent to 1, we will have p of 1 is equivalent to a naught plus, you will have here a sub 1 times x, which is 1, plus a sub 2 times 1 squared. So we will have a naught plus a1 plus a sub 2, which is equivalent to your p of 1, the function, which is equivalent to 4. And then doing the same thing, we will have x is equivalent to 2, so that we will have a naught plus, you have here 2a sub 1 plus 4a sub 2, which is equivalent to 0. And then we will have a naught, that is p of 3 is equivalent to a naught plus 3a sub 1 plus 9a sub 2, which is equivalent to 12. Now we will have the system of a linear equation, 3 unknowns in 3 equations. So we already were able to set up the system of equation, and all we need to do is to solve it using Gauss-Jordan elimination. So again, you can simply form the augmented form of the matrix, which will be, okay, do we have that one in the next slide? Let us see. So if we are going to find the augmented form of the matrix, what do we have? Can I write it here? So say, since we already set up the system of equation, The augmented matrix is given by 1, 1, 1. And then we will have a 1, 2, 3. And then we will have your 1, 4, 9. And the constant terms being 4, 0, and 12. By applying the elementary row operation and converting this augmented matrix into reduced row echelon form, we'll be able to find that the solution A naught will be equivalent to 24, A1 to be negative 28, and A sub 2 to be equivalent to 8. And then substituting it into the model, we will have P of X is equal to 24 minus 28X plus 8X squared. Now let us try to apply this concept of polynomial curve fitting in the next example. Okay, so by the way, this is the graph. So we will have a quadratic function given by this parabola. So this is another application of curve fitting. Find a polynomial that relates the periods of the 3 planets that are closest to the sun to their mean distances from the sun as shown in the table. Then use the polynomial to calculate the period of Mars and compare it to the value shown in the table. So we have here the mean distances are in astronomical units and the periods are in years. So we're given the mean distance as well as the period. So let's say the mean distance will act as our independent variable, and let's say period will be our dependent variable, and we will have several ordered pairs. That means when the mean distance is 0.387, the period is 0.241, referring to the planet Mercury. And for Venus, we will have the mean distance from the sun of about 0.723, and the period will be 0.615, and for the Earth, that will be 1 and 1, and for Mars, that will be 1.524 and 1.881. So we can consider the set, we can consider the following as simply ordered pairs. So by, again, applying the same procedure, just like what we did earlier, we say the model will be a quadratic polynomial function. P of X is equal to A naught plus A sub 1X plus A sub 2X squared. So we only need to satisfy this function by the given value of X and Y. So say P at 0.387. So here P at 0.387 is equivalent to A naught plus 0.387 of X, 0.387 of A sub 1, and then we will have plus 0.387 square times A sub 2. So we have this one is equivalent to 0.241, and with 0.723 and 0.615, we will have the equation A naught plus 0.723 A sub 1 plus 0.723 squared times A sub 2 equivalent to 0.615. And then finally, with the last point being 1 and 1, we simply have A naught plus A1 plus A2 equals 1. So with this given system of equation, all we need to do is to form the augmented form of the matrix and apply your Gaussian elimination with back substitution, or simply proceed with Gauss-Jordan elimination to come up with the reduced row echelon form of the matrix. So the solution is as follows. We'll have A naught to be about negative 0.0634, A1 to be 0.6119, and A sub 2 to be 0.4515. Substitute this into the polynomial function, and you will have this particular equation. Now, if we have P of X equivalent to negative 0.0634 plus 0.6119x plus 0.4515x squared, and let's say we want to find the value of the function when x is equivalent to 1.524, we only need to replace x by 1.524 as well as for x squared as 1.524 squared. So we'll be able to use this particular function to predict the value of the period for a given value of the mean distance. Now that will be equivalent to 1.918 years. Okay, so we can actually find the graph and we see the following. We have your Mercury, which is of course closest to the sun, followed by Venus, and then Earth, and then Mars. Note that the period of Mars, which is shown in the table as 1.881 years. The figure below provides a graphical comparison of the polynomial function to the values that are shown in the table. Okay, so we are actually trying to compare the result of the model, okay, with the actual values. Now, we can also apply our knowledge on solving systems of equation in network analysis. Networks are composed of branches and junctions and are used as models in such fields as economics, traffic analysis, and electrical engineering. In a network model, you assume that the total flow into a junction is equal to the total flow out of the junction. So somehow, this reflects the conservation principle. For example, we will have in figure 1.6 a network, and we're asked to set up a system of linear equation that will represent the network. So, and then solve the system. Now, what we can do here is to mark the junction. So the first thing that we need to do is to mark the junction or nodes. Say here, this is junction 1, junction 2, junction 3, 4, and 5. And then we apply the conservation principle. That is, inflow will be equivalent to outflow. Okay, so applying the conservation principle, you will have inflow is equivalent to outflow. Say at junction 1, so what happens at junction 1? We see here that the inflow is actually 20 and the outflow is given by x sub 1 and x sub 2. So we can write there x sub 1 plus x sub 2 is equivalent to 20. Now let this be our first equation. Let's say at junction 2, say we will have at junction 2, inflow would be x sub 4. Say at junction 2, we will have an inflow of x sub 4 and an outflow equivalent to x sub 3 and 20. So we will have x sub 3 plus 20, or say we will have a negative x sub 3 plus x sub 4 is equivalent to 20. Let this be our second equation. And again, for, let's say at junction 3, what will be the inflow? We will have x sub 2 plus x sub 3. X sub 2 plus x sub 3 is simply equivalent to 10 plus 10, or that's equivalent to 20. Let this be our equation 3. And for at, say at junction 4, okay, at junction 4, what do we have? An inflow of 10 and x sub 1. So we will have here x sub 1 plus 10 is equivalent to x sub 5. So let this be our equation 4, or improving that one, we can rewrite it as x sub 1 minus x sub 5 is equivalent to negative 10. So let this be my fourth equation. And finally, at junction 5, okay, we will have the inflow as x sub 5 plus 10 is equivalent to x sub 4. or that will be negative x sub 4 plus x sub 5 is equivalent to negative 10. Let this be my equation 5. Now, combining everything, now let us have that one so we can have the system of equation. Then we will have your x sub 1 plus x sub 2 equivalent to 20. And for equation 2, we will have a negative x sub 3 plus x sub 4 is also equivalent to 20. Equation 3, we will have x sub 2 plus x sub 3 equivalent to 20. And for equation 4, we will have x sub 1 minus x sub 5 is equivalent to negative 10. And finally, we will have negative x sub 4 plus x sub 5 is equivalent to negative 10. Now, rewriting everything into the augmented matrix. So what do we have? We will have 5 equations in 5 unknowns. So say we will have here 1, and then 0, 0, as well as 1 and 0. And then we will have 1 for x sub 2, 0 here, and then we have 1, and then again that will be 0, and then we also have 0 here. For x sub 3, this is 0 here, and then we will have negative 1, positive 1, and then 0, and then 0. And for x sub 4, we will have here 0, and then 1, and then 0, and then again another 0, and negative 1. Finally, for the coefficients of x sub 5, so we have here 0, 0, 0, negative 1, and positive 1. And of course, the constants, which are 20, 20, 20, negative 10, and negative 10. Now, since we're able to set up the system of equation as well as augmented matrix, we are ready to apply our Gaussian elimination with back substitution, or proceed with backward phase so that we can convert the matrix into a reduced row echelon form via the Gauss-Jordan elimination. Okay, now let us see what will be the result of this solution. So as you can see, this will be the model. Okay, this will be the system of equation. So we have here the conservation principle at different junction, and we come up with the augmented matrix for the system. And then by applying Gauss-Jordan elimination, the reduced row echelon form will have the following. Notice that we ended up with a row of zeros, okay, which, okay, we were able to see here. This signifies, so whenever we ended up with a row of zeros, this signifies that the system will have infinitely many solutions. So it's understood that the column 1 is a coefficient of x sub 1, and then column 2 are coefficients of x sub 2, column 3 are the coefficients of x sub 3, column 4 are the coefficients of x sub 4, and column 5 are the coefficients of x sub 5. If you're going to look at row 4, okay, if you're going to look at row 4, we will see here that we will have x sub 4, okay, x sub 4 minus x sub 5 is equivalent to 10. So basically, it seems that x sub 5 can be treated as a free variable so that we can express x sub 4 in terms of x sub 5, or that will be 10 plus x sub 5. Okay, so you see here x sub 4 minus x sub 5 is 10. So that means we can express x sub 4 as 10 plus x sub 5, and then we are going to treat x sub 5 as a free variable and allowing it to be equivalent to a parameter t. So let's say t is any real number for now. Okay, since, okay, so let's say we don't know the restriction yet for t. All we know that t is, it can be a number, right? Any real number. So looking at row 3 now, okay, we see the expression that x sub 3. So with row 3, we see that x sub 3 minus x sub 5 is equivalent to negative 10. So that x sub 3 is equivalent to negative 10 plus x sub 5, or that will be x sub 3 is negative 10 plus t. Okay, so you have your x sub 3 minus x sub 5 is negative 10. Or since x sub 5 is t, then x sub 3 is negative 10 plus t. And then considering your row 2, we will have x sub 2 plus x sub 5 is equivalent to 30. So here, x sub 2 plus x sub 5 is 30. Therefore, x sub 2 is simply 30 minus x sub 5, or 30 minus t. And finally, for your row 1, we will have x sub 1 minus x sub 5 is equal to negative 10, or that x sub 1 is equivalent to negative 10 plus x sub 5. So if you're going to show the solution, or this is equivalent now to negative 10 plus t, so this will be your x sub 1. So x sub 1 now is negative 10 plus t, x sub 2 is 30 minus t, x sub 3 is negative 10 plus t, and x sub 4 is equivalent to 10, that will be, okay, what is x sub 4? That is simply 10 plus t, right? X sub 4 is simply 10 plus t. And then, of course, x sub 5 being t. Okay, now let's see our answers here. So where t is any real number, so this system has infinitely many solutions. Now, another type of network is exhibited, or we can have this network also in electric circuits. No, electric circuit is an example of a network, of an electrical network, and normally we can apply the analysis. We can apply the analysis So another type of network would that be of an electrical network. An electrical network is a type of network where analysis is commonly applied. An analysis of such a system uses two properties of electrical networks known as Kirchhoff's law. So according to Kirchhoff, all the current flowing into a junction must flow out of it, and that the sum of the products, that is I times R, where I is current and R is the resistance, around a closed path is equal to the total voltage in the path. So in an electrical network, current is measured in amperes, or okay, we can write that one as A. Resistance is measured in ohms, okay, given in the symbol omega. And the product of current and resistance is measured in volts, which is denoted by capital V. Okay, we have here this symbol which represents a battery. The larger vertical bar here denotes where the current flows out of the terminal. The symbol, okay, we have here a zigzag, denotes resistance, and an arrow in the branch shows the direction of the current. Say, for example, we will have this electrical circuit. Determine the currents I sub 1, I sub 2, and I sub 3 for the electric network given below. So the first thing that we need to do is to come up with the conservation of the current. Okay, according to rule number 1, all the current that is flowing into a junction must flow out of it. So if we're going to take a look at this figure, we will have, say, junction 1. We can see that I1 and I2 enters junction 1 and leaves as, I1 and I3 enters junction 1 and leaves as I sub 2. So that we will have I1 plus I3 to be equivalent to I2. Now, the second condition, according to Kirchhoff, is that the sum of the products IR around a closed path is equal to the total voltage in the path. So we can see here that we will have this direction. We can have I1 times R1 plus I2 times R2 will be equivalent to the total voltage, which is 7. Okay, so we will have here I1 times R1, as well as plus here, you will have your I2 times R sub 2 is equivalent to, so you have here that loop is equivalent to 7 volts. Now, as you can see, I1 times R1, and R1 is 3. So that means we will have your 3I1 as well as 2I2 is equivalent to 7. So again, let this be our equation 1. Let this be our equation 2. Now another loop will be at the second, okay, we will have here the second portion, or the lower portion. So again, we will have I3 times R3 plus I2 times R2 to be equivalent to 8 volts. Okay, so we will have here I3 times R3 and then plus I2 times R2 equivalent to 8 volts. And since R3 is 4, so we will have 4I3 as well as 2I2 is equivalent to 8. Let this be our equation 3. So we're ready to set up the system of linear equation. Let us summarize that one. So the system of equation will be I1 plus I3 is equivalent to I2. Or let's say that will be equivalent to 0. Okay, so since we will have a 3 unknowns, I1, I2, and I3, so we can express equation 1 as I1 plus I2 plus I3 equivalent to 0. And then for equation 2, we will have your 3I1 plus 2I2 is equivalent to 7. And we will have here 2I2 plus 4I3 equivalent to 8. Or the augmented matrix. So what will be the augmented matrix? The augmented matrix will be 1, 3, 1, 3, 0. And then we will have 1, and then 2, and then 2. And for I3, we have your 1, we have your 0, and then 4. And they're all equivalent to 0, 7, 8. Now, since we already have the augmented form of the matrix, we can simply apply our Gaussian elimination with back substitution, or proceed with the backward phase, so that we will have the reduced row echelon form of the matrix via the Gauss-Jordan elimination method. So let's check our answer. So here we'll be able to see first applying the first law of Kirchhoff, wherein we find the conservation principle, and then doing the balance among the loops, and come up with a system of linear equation in 3 unknowns, transforming that one into the augmented matrix, as well as the reduced row echelon form, Obviously, this tells us that we will have a unique solution. That is I sub 3 is equivalent to 1, I sub 2 equivalent to 2, and I sub 1 equivalent to 1. So the system is consistent, independent. Okay? So we see how we can model real-life problems, which are actually systems of linear equation, and such as in polynomial curve fitting, and then network analysis. With all these problems, we already at least know that we can solve them using the principles of linear algebra.